Good morning, my dear students. Welcome to this session on moment distribution method, Unit 4 of JNTUK syllabus of structural analysis 2. So, last session we have now talked about this procedure in detail, step by step procedure, how you have to follow each step and what calculation is involved in each step to uh, finally solve uh, with an example of continuous beam also. Okay, just to have a clear idea, I've explained with that example. Right now, let us see once again in a quick manner, quickly, just step by step calculations. I'll just tell you. So first, given beam must be made into fixed beams. Given structure, you have to convert that into fixed beams and calculate fixed end moments. That's the step one. Next, calculate distribution factors for all the members at a particular joint. Identify joints. How many joints are there? At all the joints, you have to find distribution factors. Okay, that is step two. Step 3, you will find some unbalanced value at the joint, unbalanced moment. You will find at the joint that must be balanced by distributing the balancing moment to various members meeting at the joint proportional to distribution factor. Okay. Right. So once you distribute the balancing moment, and that will be carried to the far ends if the far ends are fixed. Okay, that is the next step. So, right. So distributing the balancing moment, the balance remaining at the joint, that is the third step, right? So once you distribute the balancing moment, then the next is to carry that to the far ends. Okay, that will make the balanced joints to become unbalanced again. Okay, so repeat again balancing. So you have to balance them again. Once you balance, again you have to carry over to the far ends. So likewise, this process will be continued. It is like a loop. Okay, so you balance the joint and then carry over moment will disturb it. So again you will balance it and then again carry over moment will disturb that balance. So likewise, you have to proceed to so many cycles, so many trials you have to make to get the balance value almost nearer to zero. You can't get to zero because it needs plenty number of trials. Okay, so you have to set some value of convergence, then achieve that convergence and stop the process. Okay, so that is how it is. So mostly in most of the cases 4 or 5 trials are enough to go to the required convergence. Okay, so once you complete this balancing process, then you calculate the end moments by adding all the moments at a particular end. Okay, that will give you final end moments. This is the procedure in short. Okay, let us see with an example. So here is a problem given to analyze the continuous beam by moment distribution method. Draw BMD, SFD, also draw elastic curve. Okay, right, this is the given problem. Right, so AB, BC. ABC is a continuous beam with ends fixed. Right, B is a hinge. So 6 meters with moment of inertia 3I, 6 meter span with moment of inertia 2I. AB has got UDL, BC has got point load which is eccentric. Okay, right. Come back to the step 1. So fixed end moments are to be calculated. Okay, so step 1 is to calculate fixed end moments. Right. So what I told you to do it by fixing the members. So AB is a member. So you make fixed end moment. Right. So fixed AB is fixed. Thirty kilonewton meter. 30 kilonewton per meter. UDL value 6 meter span. So what are the fixed end moments for a fixed beam with UDL WL square by 12? So how the moments will be? Direction. So these are the fixed moments directions. So all these we have been discussing right from the slope deflection method. Why such directions we shall give all that. So left support anti-clockwise, right support clockwise. Okay, because the beam is going to bend like this. Okay, this is how it is going to bend. Right. So this is anti-clockwise. That's why I wrote minus. So all the anti-clockwise moments we will be writing negative. This is followed from slope deflection method itself. So WL square by 12 you calculate. W is 30, L is 6 by 12 is minus 19. So B is clockwise positive. WL square by 12 again, 36 square by 12, so 90. Coming to BC, so make the beam as fixed beam. Right, so at 1/3, right 1/3, you have a point load, 72 kilonewton. This is 4 meters from left and 2 meters from right. So B and C. So MFBC. See the notations that I am using. MFAB, fixed end moment. AB I wrote means I am writing the value at A. Again MFBA I am writing the value at B. Similarly MFBC, MFCB I am writing the value at B. I am writing the value at C. Okay. So again, same notations, left anti-clockwise, right clockwise. So left anti-clockwise means negative sign. The value is PAB square by L square is the fixed end moment at left end. P is 72 force point load. A means 4 meters. This is A is equal to 4 meters. This is B is equal to 2 meters. So A B square by L square. L is 6 meters. Total span 6 minus 32. And again, from the right end, CB, MFCB, clockwise, so positive. The moment formula is P A square B by L square. Okay, load into opposite distance square. So 4 square into 2 nearer distance divided by L square, 64. So these are all the fixed end moments that are to be calculated. So with this, step 1 is done. Got it? So next, going for step 2. Right. So let us see the step 2 here. So step 2, if you see that distribution factor shall be calculated for all the members meeting at the joint. Okay. So how many joints are there here? There is only one joint B. Okay. This is a joint B. So you have two members BA and BC. So try to prepare this table as it is. Okay. So that it will be easy for you to work out the distribution factor. So first write the joint, then write the members BA, BC. Then go for K calculation, stiffness value of BA. So 4EI by L is the formula. K is equal to 4EI by L is the formula. So 4 times E not given, keep it as it is. And I is given as 3I, substitute that, by L is 6. So that will be 2 times EI. Similarly, BC, 4EI by L, same formula. Reason why I am using 4EI by L? Because if you see B is near end. So whatever you write, first letter is near end and the second letter is far end. So in case of A is far end. So A is far end fixed. If B is near end, where you are calculating distribution factor, A becomes far end. So, and also C is far end. So A far end, C is far end. So A is fixed, C is also fixed. So if the far end is fixed, I know the stiffness value for EI by L. So that's how it is. So 1.33 times EI. Okay. Now what? Add all the stiffness values at a joint. So how many you have? Only two. So 2 plus 1.33. So that is 3.33 times EI. This is joint stiffness. These are all member stiffnesses. Okay. Now what is distribution factor is equal to K divided by sigma K. Okay. If you want, you can write all these formulas. It will be still clear to the examiner, right? Okay. So what is this now? K by sigma K. What is K of BA? 2EI. Okay. So this is 2EI divided by 3.33 EI. So that will be 0.6. So anything more than 2 decimal places, you just round it off to 1 decimal place, right? Same way for BC, distribution factor is 1.33 times EI divided by K divided by this sigma K. So 1.33 divided by 3.33, that is 0.4. Okay, so got it. So step 2, distribution factor table must be completed. Means what? You have to calculate distribution factor for all the members. Okay, right. What next? After you calculate the distribution factors, now what? Balance the joints where you have unbalanced moments. Okay. Right. To do that, I am again using one more table called distribution table. Okay, we will do all these balance carry over, again balance carry over, everything in this table. Okay, so let us perform this. So try note these tables. Okay, as it is, you are going to use it for any other example. Right. So how to prepare distribution table? First, you leave one column for all the activities that you do to note activities. Next, the first row will be the topmost row will be we will be mentioning all the ends of the structure. So we have end A, end B, and end C. Okay, right? So now the first row is over. Then you draw a line like this, and you draw a line at the middle of B so that B is at the middle. So to the left of that line it is BA, to the right of that line it is BC. So B is a joint, that's why it should be, you have to draw a line exactly under B. Okay, now you draw at the end after C. Here it is before A and after C. Right. So that completes the first row. Okay. Got it? Okay. Next. The distribution factors you mention first. Okay. Distribution factors you have to mention first. So what are all calculated distribution factors? Distribution factor for BA is 0.6. You write that. This is BA, right? And distribution factor for BC is 0.4. You write that one. Okay. And A you don't have distribution factor, and C you don't have because they are not giants, right? So only B is a giant. We have distribution factors. Next, fixed end moments you write next. Second, third row. First row, the nodes are noted. Second row, distribution factors are given. Third row, fixed end moments you will write. You see what are all fixed end moments? Just write it in the order: minus 90, plus 90, minus 32, plus 64. Minus 90 at A, left of B, plus 90, right of B, minus 32, then C 64. Right? MEFAB minus 90, MEFBA plus 90, MEFBC minus 32, MEFCB 64. So once you write these fixed end moments, now come to joint B, this joint. So what is total moment at this joint? 90 minus 32. Okay. So 58 is the total moment at B. Sigma MB is equal to 90 minus 32, 58. Okay. Right. So what you do with that 58? It should be 0, right? Total moment at B shall be 0. Reason what? B is a hinge. Okay, total moment at P should be 0, but it is not 0, it is 58. So what you do now? You have to balance this remaining value. That is remaining value. So to make it 0, you have to add minus 58. So be careful with this. Please concentrate. Plus 58 is remaining, and I am adding minus 58 to make it 0. So now what is total value? 0. So you are adding minus 58. So where to add minus 58? Is it to this side or this side, or how much to the left and how much to the right? So what you do, minus 58 into zero point 0.6 distribution factor will be the moment share of BA. Okay, distribution. Okay, moment distribution. So you are distributing the moment. This is the title of the method. Moment distribution. Okay. What moment distribution? Balancing moment. Okay. This minus 58 is called balancing value. Balancing what? Balancing plus 58. It is balancing plus 58. Okay. It is balancing the giant B. So minus 58 into zero point 0.6 will be minus 34.8. Again, minus 58 into 0.4, the share of BC, okay, will be minus 23.2. You have to write it in the next row. What is called balancing? What we call that? Balancing. Okay. Now you add total moment at B. If you add this total moment at B, this total is plus 58. What is this total? Minus 58. Plus 58 minus 58, 0. Got it? So this is how we balance it. Now, what you have done, you have applied minus 34.8 at B for AB. What is far end of that one is A, which is fixed. So half of this value shall be carried to A. B is near end. Wherever you have applied moment, that is called near end. That is the other end is far end. A is fixed. So half value should go to this. You have to draw arrow like this. This arrow must be there in your table. Okay. This is not for my purpose. Not for my presentation purpose. This is part of your answer, right? So your solution, part of your solution, you shall draw this arrow from here, from this row to this row. Okay. So this half of this value is carried. So what is half of this one? Minus 17.4. Same way, minus 23.2 is applied at B for BC, and C is far end, which is fixed. So half the value should be taken to this one. So minus 11.6 to C. Okay, got it? So this is called carryover moment. So that is another row, carryover moment. Okay, so that's all. As already told, the fixed end need not be balanced because it is self-balancing. And also the C is also self-balancing, you need not balance it. Only giant B is to be balanced, and that's all. Okay. So you don't have one more trial. What is the reason? You have only one giant, and if there is nothing to carry from other end to B, which will be disturbing the balance of B. Okay, nothing comes from A and nothing comes from C because they are not giants. B is the only giant. Okay, so that's why moment will not come from A to B or else C to B. So that's why you can stop this process. Okay, right? So now what? The last row will be final end moment calculation. Okay. So what you do? You add all the values in this row. Okay. So what do you have? You have fixed end moment. You have carryover moment. Add all those. This is your final MAB value. Similarly, you add these values, this value and this value. Don't add this distribution factor by overlook. Add only the moments, not the distribution factor. So plus 90 minus 34.8, 55.2. Same way, minus 32 and minus 23.2, again minus 55.2. So this is plus, is minus, total is 0. Same way, C, you add this value and this value, that is 52.4, is moment at C. So these are all end moments, MAB, MBA, MBC, MCB values. Okay, so this is how we complete moment distribution process, and we will have uh, end moments MAB, MBA, MBC, and MCB values. Okay, right. So with this, we have completed moment distribution process, and we are still pending with to draw BMD and draw SFD. Okay, we will take up this in the next session. Right. Thank you.